Next up, so excited to welcome to the stage CEO and founder of Jonah Health, a man who's worked around AI and healthcare probably more than anyone else in the industry, to give us a little bit of a glimpse into the future. Leo Grady. Leo.
Thank you, everybody. So I'm Leo. I do AI. Hey, can I grab the clicker? Thank you all for coming out on a Tuesday night. When Joe asked me to give the talk, I thought about the fact that right now Jonah's still in stealth, and so I thought, is this really the right time to give a talk? But I'm really excited about what we're doing, and I thought I would probably shouldn't show you guys all everything that we're doing, but it'll be fun. This is the first time I'm giving a talk and showing some of the work that we're doing at Jonah. My history with AI is really long. I did a PhD in AI 20 years ago in computer vision, and I've spent my whole career in healthcare. And started at Siemens, building AI applications in radiology, and then at HeartFlow, building AI applications in cardiology, and then I was CEO here in New York of Page AI, building applications in pathology. So at HeartFlow, we had the first AI product that Medicare ever paid for. It was a big milestone in the industry. And Page, we had the first FDA approval for an AI system in pathology. During that time, I also filed over 300 patents as an inventor, and I even wrote 2 books on AI. So, with the holiday season coming up, you can put these on your list after Juliette's book. So I've been in the industry for a long time, and I feel that AI has an incredible opportunity to really impact healthcare, and I've seen it firsthand with these different products, with all of these different technologies that we've built over the last 20 years since I did my PhD. So what I'm going to do is I'm going to tell you about Jonah. Before I do that, I'm going to talk a little bit about what we've done at some of these other companies, at HeartFlow, at Page, to give you a sense of how AI is being used in healthcare today. And so starting off with HeartFlow, we were building a cardiovascular diagnostic test that was purely non-invasive. And it was a combination of AI and computational fluid dynamics. It was a company that came out of Stanford, based in the Bay Area. And what we did is we took a cardiac CT, a CAT scan of your heart, and from that CT, we extracted all of the center lines from all of the coronary arteries. Then we found all of the disease, all of the plaque. Then we extracted all of the lumen, the area that the blood flows through. From that, we also extracted the heart muscle, the myocardium. And we created a 3D computational model that was personalized for an individual. And we used computational fluid dynamics to calculate blood flow through the coronary arteries. And from that, we could tell whether the person needed a stent or not, whether this was a functionally significant stenosis in the coronary arteries. We did multiple clinical trials. We had FDA approval as a de novo. We had a NICE recommendation, if you know what that is. We launched this product in North America, Europe, and Japan. After that, I moved out here to New York, where I was CEO of Page AI. And Page was a spin out of Memorial Sloan Kettering, where we were building AI applications in pathology. We had an exclusive license with MSK to build with all of their pathology data. And I had 10 people up in the Bronx scanning pathology data day in, day out for 2 years, pulling these slides out of the archives, cleaning them, scanning them, so that we could use that data to build AI models that could really find cancer and do a lot of things that can help pathologists in a number of ways. Now, you may not know much about pathology. It's really, you're taking tissue out of a patient, looking at it under a microscope. It can be a biopsy, it can be surgery. But what you may not realize is that today, pathology is almost entirely microscope driven, right? So when a pathologist gets a tissue sample, they mount it on a slide, they wheel a cart around the pathology lab with books of slides, they hand them out to the pathologist. This is state of the art today. They look at it under a microscope. And so in order to use AI, you need to first digitize all of the slides, which means you have to have these scanners, and you can't even launch the AI systems unless the entire workflow changes to digital. So in order to not only build these clinical grade AI systems, but to actually deploy them, we had to build the entire infrastructure. We built digital slide viewers, digital slide storage. We had to deal with all of the different scanner types. We had to get this platform FDA approved just for the viewing and the digital diagnosis of it. And then on top of that, we could build these AI products. So as I mentioned, the first FDA approval for an AI system in pathology was for Page Prostate. This was an AI system where we automatically found prostate cancer in a needle core biopsy. And it happened a lot that people have, a man will go in for his checkup, get a PSA value, it's high, they do a bunch of prostate needle core biopsies, 80% of them are negative. The guy doesn't have any prostate cancer, but it takes pathologists 30 minutes, an hour sometimes to look through all of that tissue. And sometimes it's easy to miss a very small focus of cancer. So this technology is used in conjunction with the doctor. It's not a fully automated system. We did clinical trials, and what we found is that when the pathologist, so we had the pathologist do the diagnosis normal, then they did the diagnosis a second time using Page. And what we found is that when we compared those two, using the AI system, the pathologists had a 76% reduction in false negatives, missed cancers, and a 24% reduction in false positives, overcalled cancers. And they also went faster. And what was interesting about that was that we tested 26 different pathologists using this technology, a whole range of different people. Some of them were very experienced, some of them were right out of residency. Some of them were specialists in prostate cancer, some of them were not. And what we found is that they all got better, but the ones who are not specialists got better the most, and the ones that were less experienced got better most. And so not everyone has the privilege of going to Memorial Sloan Kettering to have a pathologist look at their slides. But the fact with technology like this, everyone can get their slides read by a pathologist that is up to those same standards. But, again, building AI itself wasn't enough. We had to actually innovate not only on the platform and the storage and the work list and all of these things, but even on the visualization of displaying the AI. So here you see this marker that obscures the tissue. So pathologists are trying to look at this stuff really fast. They can't see through that marker. So we actually had to innovate on the visualization side too, to highlight the areas of cancer, but not obscure the vision of the pathologists. So that's what we were doing at Page. And the entire industry, I did my PhD, like I said, a long time in computer vision. Computer vision matured much more rapidly than many other areas of AI. And what we've seen in the last few years is this real rise of computer vision maturing, and now large language models getting better and better. NLP was much slower to mature than computer vision. But just in the last few years, you see this explosion in the size of these models, these large language models, getting larger and larger and larger, and they can do more things. And the use of large language models in medicine is so far much less mature and much less advanced than what we've seen with computer vision. However, there are no applications that people are working on or that are already deployed. So one of the first applications of NLP or large language models in healthcare was for dictation, for doctors to dictate a report and have that report automatically transcribed. Things like radiology, pathology, nuance. This was really like their core product, the Dragon, for a long time. But the ability to now listen to a doctor's office visit, to autofill in the EMR. You see companies like Suki and all working on this sort of thing that can really help fill out all of the administrative work of a doctor so that they can spend more time focused on the patients. There are a lot of companies working on prior auth as an application of large language models. I'm very skeptical of this application, but we can talk about that over a drink later. And a lot of doctors are known for talking to Dr. Google, looking things up. Maybe large language models can be more effective. And just in the way that OpenAI is threatening Google with search, these large language models can be more effective for informing doctors than Google is today. But a lot of challenges with that application. And then the last one that we hear about more, but I think is further off, is actual patient engagement with these chatbots to actually learn more about healthcare and about their medical history and so on. But to be honest, I'm not excited about any of these applications. So let me tell you what I am excited. Some of the most interesting areas of medicine today are extraordinarily complex. Proteomics, metabolomics, transcriptomics. If you get one of these samples for a patient, the doctor is overwhelmed with data and they have no idea what to do with it. And yet we see all of this amazing research happening, showing the value that this sort of testing can really bring to understanding the disease of a patient and also the best treatment for those patients. But the complexity is overwhelming. And what's worse is that the science is rapidly increasing and rapidly expanding. But I mean, you see this is the number of publications in PubMed from 1950 to 2014. Good luck, trying to keep up with all of this. And the complexity of the areas of medicine are dramatically increasing. The complexity of the scientific research is increasing. And it's a good thing. It's a good thing that we have more research. It's a good thing that we have more trials. How do we actually make use of it in order to better care for patients? So let me tell you about what we're doing at Jonah. We are focused on one of these areas of medicine, the microbiome specifically, which I believe will be the next revolution in healthcare. The microbiome is all of the organisms that live in your body and on your body. Just some stats here. The number of organisms that live in your body outnumber your human cells by about 3 to 1. And if you were to collect all of the genetics within all of those organisms and compare it to the genes in your human cells, it's about 1,000 to 1. And by the way, it changes too. And so talk about complexity, lots there. But what's really exciting to me is that the microbiome has been shown to really underpin your health across so many different aspects of medicine. We think of it a bit in GI, Crohn's disease, colitis, bowel syndrome, celiac disease, food allergies, for sure, absolutely. Autoimmune conditions as well, chronic fatigue syndrome, multiple sclerosis, lupus, asthma, and more. But the microbiome has been shown to go really beyond these areas. Obesity, how your body processes food, the caloric intake that you get from eating different foods. Cancer, not only the genesis of cancer, but actually which treatments are going to work better for which patients. The gut-brain axis, 90% of your serotonin is produced in your gut, 50% of your dopamine. The microbiome has been linked to Parkinson's, Alzheimer's, but also mental health, depression, anxiety, bipolar disease, schizophrenia, skin, acne, psoriasis, all of these inflammatory disorders, liver disease, cardiovascular disease, even performance, longevity, healthy aging, athletic performance is modulated by your microbiome. So incredible complexity and also incredible connection to the rest of your health. So it's complex. Consumers are interested in it. People spent $54 billion last year globally on probiotics, on kombucha, on kefir, on all those things you guys see in Brooklyn. And the fact is that you can get microbiome tests. People order them. You can buy these right now. But they get things like this. This is considered the gold standard of microbiome tests today. It's called GI map. There's a cash pay test, $450. People spend it out of pocket. And then they get a big long list of species told you're high, you're low. Some of these companies then follow it up and say, I've got the perfect probiotic for you. Many of the people that order these tests, though, then they post it online. They say, what does this mean? We see these on Reddit every day. They bring it to their doctor, and they say, what does this mean? But what they don't realize is their doctor doesn't know what it means either. So when I show this to doctors, GI docs, they say, yeah, I see these every single day. I have no idea what to tell somebody. And how could they? Because the literature is exploding at this blistering pace. This is microbiome in PubMed publications every year. You do the math, that's more than 2,000 papers a month published on the microbiome. No human being can read all of these. But this is where we have an opportunity with large language models. So what we're doing at Jonah is building a large language model that can read all of this microbiome literature and use it to interpret these complex tests to help people understand, to help patients, help doctors understand what is known about their microbiome today and how they might influence it for the better. You guys want to see a demo? All right, so this is the first time I'm going to do this live. And so I don't know how it's going to go, but let me try. So what we do is take those tests. We run it through our AI system. We spend a lot of time validating that the AI system has read the literature correctly. And then it starts with a generative AI output, which you can't see. Let me bring, yeah. So it looks like this. You can't read it back there, but it's a lot of text. And what this is, like what I showed you before, that GI map, which is a big long list of species, this is a plain text summary of what's known about this person's microbiome. Now this is for a fictional person, Sarah, and this is a plain text summary of all the key findings that were found in Sarah's microbiome, all of the things that she should pay attention to, and some actions. But Sarah can go deeper, or her doctor can go deeper. And what this is saying, maybe you can see it, maybe you can't. What this is saying is Sarah's microbiome strongly matches what's been observed in the literature, the profile for Crohn's disease. Sarah's microbiome also partially matches what's been observed in the literature for ulcerative colitis, partially matches what's been observed in the literature for irritable bowel syndrome type D, partial match with atopic dermatitis, eczema. Sarah's microbiome has been found in people with egg sensitivity, shellfish sensitivity, and also linked with lactose and gluten intolerance as well. Sarah's microbiome has been strongly linked with joint pain and depression, and it's also been associated with diarrhea, abdominal pain, bloating, and so on. Now, in terms of what you can do about it, for example, a ketogenic diet is known to shift your microbiome in certain ways. But for Sarah, a ketogenic diet would shift her microbiome in ways that would actually amplify these negative associations. So it's something she wants to avoid. In contrast, a low-fat diet would shift her microbiome in different ways. And for Sarah, a low-fat diet would shift her microbiome in ways that would actually mitigate, improve a lot of these negative associations, and so on and so on. Certain probiotics might benefit her. Certain probiotics may not. We don't sell probiotics. We're just totally neutral here. Aspirin changes your microbiome in certain ways. For Sarah, it might amplify these negative associations. Now, if she wants to go deeper, she can click in any of these areas. So, for example, Crohn's disease. What this is showing is here are all the organisms that have been linked with Crohn's in the literature. Here are the ranges. Here's what was measured for Sarah. And here are the scientific publications that have linked these organisms with Crohn's. And these papers are ranked in order of quality. So large studies, high quality journals are on top. Smaller studies, lower quality journals are on top, on bottom. Sarah can go even deeper. She can go click on this paper. It highlights these 4 organisms that were studied in this paper. The study size was 2,045 subjects. She can go out to PubMed, link out, go read the paper. In the future, we're going to actually allow her to talk to the AI and interact with it, ask it questions about the paper or her microbiome, or go even deeper. So Sarah can go as far down the information hole as she wants to here, or she can just stay at the high level and see the summary of what was extracted out of the literature. So one more comment here is this is a demo. This was done a few months ago. At that point, the AI system had read about 50 papers in the literature. We've dramatically expanded that, and the AI system is reading the whole literature. And we have a human team that's really validating that each one of those papers is being read correctly and interpreted correctly, so that we can really stand behind anything that we say. The second is that if you're Sarah and you look at this and you say, okay, well, ketogenic diet, bad, low-fat diet, good, high soluble fiber, good, how do I actually implement this? Put this into practice in my life? How do I fit this into my work schedule, etc.? We're actually going to also offer her access to a dietitian so she can actually talk to somebody and really help work through some of this going forward. All right, that's the demo. And thank you. Was that all right? First live demo. And that's the end of the talk, actually, too. So thank you.
Thank you, Leo. Please stay up here. We have 5 minutes for Q&A. On behalf of Ashkenazi Jews with stomach issues everywhere, thank you so much. All right, have any questions for Leo?
Hi, Leo. How you doing?
Wonderful.
This is a great talk. I think what Jonah is doing is really what the future of medicine gonna be, which is individualized medicine, where different people have different needs, and then use what's fit you. I think that's a very good idea. I have questions though about the microbiome and the role of what we eat.
Mhm.
The products that we eat, for instance, have growth hormones on it. They have antibiotics on it. They have preservative that can affect the microbiome. Does the AI kind of study that? In addition to literature that deal with the changes in the microbiome.
So I think you're right on both points, right? From the standpoint of personalized individualism, you and I probably share 99.5% of the same genetics. Our microbiome is only about 10% the same. So it's very individualized from person to person. What our AI system is doing is matching the literature to somebody's microbiome and interpreting that in the context of the literature and making recommendations in the context of the literature. You're absolutely right. Hormones, antibiotics have been shown to affect people's microbiome. There's a reason that farmers give antibiotics to their animals. It's to make them fat, and it works. And yet the increase in inflammatory disorders, whether it's asthma, Crohn's, colitis, food allergies, you name it, one of the hypotheses is it has to do with the food supply. One of the hypotheses is it has to do with overuse of antibiotics, particularly in children. We don't fully know, right? There's the clean hypothesis as well, that it's just that we live in this bubble of sanitization, that your immune system doesn't really get used to some of the microbial environment. We don't fully know. As we are able to move forward and gather more data, our goal is to be able to go beyond the literature and start advancing the science and not just reflecting it. But today, we just have to live within the bounds of the science as it is today.
Any other questions? Why don't you come on up?
This is great. Thank you. I'm Juliette's co-author on the AI Dilemma, Art Kleiner. This is fascinating. And here's a naive question. You're talking about an explosion of scientific literature, of medical literature, and then making sense of it. And that's happening in microorganisms. Is the same kind of thing happening in other medical fields? And what happens when they kind of meet each other? Is there?
It's absolutely happening, right? I mean, there are areas of medicine, right? I mean, like a blood panel. We've known for a long time how to interpret that. We know what's abnormal, what's normal. All of the omics is really exploding from the standpoint of both the complexity and the literature. And so I think there's an opportunity to use a similar approach with some of these other omics. They all do converge, right? They converge in the individual. And so as we move toward personalized medicine, truly personalized medicine, we're going to need to integrate all of this information. I think the only way that we're going to make sense of it is with this kind of technology that can really synthesize complexity into something that is meaningful and actionable.
We're going to wrap up with one question from the stream. Alexandra asks, is there any validation of the results generated by the AI? Shouldn't the results need to be put into context of other individual characteristics, gender, age, comorbidities, treatments, in order to produce individualized findings?
So remember that we're not predicting somebody's got Crohn's disease. We're not saying this is not a diagnostic test. What we're doing is we're reading the literature for you and saying, here's what was found in the literature, and here's how it relates to your microbiome. And so the validation is really around, did we read the literature correctly, and are we telling you the right information? Ultimately, you have to take the scientific evidence, for yourself. And we put a quality score on every paper, which is a combination of the study size and the quality of the journal that it was published in, so that we can provide that information. But ultimately, some findings have more evidence, some have less. We just bring that information to you, and you have to decide, and your doctor, how to use it most effectively. In terms of how to personalize it to an individual, some of these studies are done on specific populations. Some of them are done on more broad populations. We don't necessarily know the impact of all of these factors yet on the microbiome, or how we should calibrate effectively for one population versus another. At the moment, unless the study is like only on children or something like that, which we're just ignoring, then we're putting it all together. But again, all of the papers are cited, and you can look at it yourself. I think as the data grows and the science grows, we'll be able to individualize it even more.